Hi everyone, my name is Simon Ray and I will present you this paper titled Almost Group Envy-Free Allocation of Indivisible Goods and Chore, written together with Harris Aziz. Okay, let's start. So the problem we're facing today is that of the third division of indivisible goods and chores. So we've got a set of agents and a set of items, and we want to allocate the items to the agents while taking into account the preferences of the agents. We assume here that the items can be either goods or chores, meaning that the agents can have positive and or negative utility to the item. And the question we are interested in is that of devising fairness criteria that applies to groups of agents in this context of goods and chores. So what we want to do is to extend the group fairness concept introduced by Konitzer et al. To the framework for goods and chore introduced by Aziz et al. Keep in mind that throughout this presentation, I will assume that the agents have edited utilities. All right, let's get started, and we will start by defining some fairness criteria for groups. And to do so, we'll start very simply with envyfreeness. So, as you might know, envyfreeness is a fairness requirement which stipulates that in an allocation, it should not be the case that an agent envies another, where envy means preferring what the other agent got. So in this very simple example here, we can draw the prefer relationship that links one agent to another if the first agent would have preferred receiving what the second agent got. So let's say the prefer relationship looks that way. So in here, the allocation is not envy-free, and to be envy-free, an allocation would require the prefer relationship to be empty. And as you probably know, envy-freeness cannot be guaranteed in the general case. So what I've been done is to introduce relaxation for it. And one of these relaxation is envy-freeness up to one item, which stipulates that we can remove the envy by deleting items from the agent's bundle. So for instance, in here, by removing the monitor from the bottom agent, we can eliminate the envy between the top agent and the bottom agent. Well, we can do the same for the second agent and for the third. Note here that because the gloves are meant to represent a chore, we can remove it from the current allocation of the agent. Okay, so that's what we want to do. But instead of doing it only for pairs of agents, we want to do it for any groups. And the next question is thus to wonder how we can do that. And what we're basically saying is that an allocation is group envy free if there are no two groups of agents of the same size, such that one envies the other. And by envy here, we mean that there exists a reallocation of the items that have been received by the agents in the envied group to the agents in the envious group that defines the Pareto improvement. So everyone is weakly better off, and at least one agent is strictly better off. And so if there are no two groups such that there is a possible reallocation that is a Pareto improvement, then the allocation will be called group envy-free. And it's easy to see that this generalizes envy-freeness, and thus we cannot guarantee that the GEF allocation exists. So what we're going to do is that we will once again relax the requirement and introduce group envy-freeness up to one item, GEF1, which stipulates that we can eliminate the envy by removing one item as before. Okay, so let's formalize that a bit. We will say that an allocation is GEF1 if for every pair of non-empty groups of the same size, for every reallocation from one group to the other, and from every agent in the groups which receive the item, there exists an item that we can remove, such that the utility profile when removing these items does not Pareto dominate the current allocation. All right, and that's the fairness criteria we study in the paper. Let us now delve a bit more into the details of our results. So first, note that when all the items are good, so they only yield positive utility, We already know that the GF1 allocation always exists and can be found in pseudo-polynomial time. That's a result from Konizer et al. But when there are chores, things are a little bit harder. Okay, let's start with natural preference restriction. That is when the preferences are identical. When the preferences are identical, we can show that any EFX allocation, and we free up to any item, also is GEF1. So if we manage to compute a EFX allocation, we would also find a GEF1. And what we actually show is that it's rather simple to compute an EFX allocation in this setting, and we can do as follows. Consider the following example with two agents with identical preferences. What we're going to do is that we will first order the item in decreasing order of absolute utility value. And then we will sequentially allocate the items, giving the chores to the best of agent and the goods to the worst of agent. So for instance, in here, the first item, which is a chore, will go to any agent. Then comes the save that is allocated to agent 1 because he's the worst off. Then the chore to agent 2 because he's the best off, and so on and so forth. And one can check that this allocation is indeed GFX, and by looking at the paper, you can see why it implies GF1. All right. We also focus on a second preference restriction called ternary symmetric preferences. We will say that agents have ternary symmetric preferences if there exists alpha I, such that the utility that the agent derives for one single item always is in minus alpha I, 0 alpha I. So for instance, these preferences are ternary symmetric. So for the first agent, alpha I would be 1, for the second 3, and for the third 5. And in that case, we also show that we can always find a GF1 allocation in polynomial time. Let me now explain a bit how we can do that. First, we will partition the items into three sets. The first set, called big O plus, will contain all the items that are subjective goods, meaning that there is at least one agent who consider the item to be a good, yielding strictly positive utility. Then comes big O0, which are the items which are subjectively neutral. So there exists at least one agent who has utility 0 for it, but no one consider the item to be a good. And finally comes O minus, which is the set of objective chores. That is, items for which every agent has negative utility for. Okay, so we have these three sets, and what we're going to do is that we will first allocate the items in the set O plus, so the subjective goods. So what we're going to do is that we'll first change the preferences such that they are binary, meaning that the utility of the single items are either 0 or 1. And using these binary preferences, we will compute a Nash optimal solution using the flow algorithm introduced by Barman and Schauer. I will not explain how this algorithm works, but basically in our example, the flow would look like that. And we will thus obtain an initial incomplete allocation. The next thing we show is that with binary preferences, any Nash optimal solution also is Lexi-min optimal. So we know that the partial allocation we've computed is Lexi-min optimal. Just keep that in mind. Let us now allocate the other items. We will do it sequentially as follows. First, we will allocate all the chores, giving each chore to the worst of agent. So in our little example, the bucket will go to agent 1 and the gloves to agent 2. And we will then allocate the neutral items, giving them to any agent who has value 0 for it. Okay, so now we've allocated all the items. Remember here that we are still working with normalized utility. So the utility of the items are within minus 1, 0, 1. And what we show is that with these normalized preferences, the way we allocate the objective chores and the subjective neutral items preserves leximin optimality. So the allocation we have here is also leximin optimal. And the next step is to show that leximin optimality implies GF1 when working with normalized utility. Um, I will not present that, but if you can find all the details in the paper. Okay, so now we've got an allocation which is GF1 with the normalized preferences, but we actually show in the paper that GF1 is preserved under denormalization. So this allocation also is GF1 with respect to the initial preferences. And so this procedure, which works in polynomial time, will always find a GF1 allocation when preferences are ternary symmetric. All right. I also want to briefly mention the fact that we show that checking whether a given allocation is GF1 is a co-NP hard problem, and that for all cases when there are only goods, only chores, or a mix of goods and chores. Okay, let me wrap up. So what we've done in this paper is first to introduce fairness concept that applies to groups of agents when there are goods and chores. We've presented its link with common fairness criteria, and we've studied its existence under natural restriction of the preferences. There is still some work to do, and the main question left open is that of the existence of a GF1 in the general case of additive preferences. Thanks for watching. I hope you enjoyed the presentation, and if you want to know more, please read the paper. Bye.